All right, let's dive right into this explainer and explore the absolute fundamental rules that govern motion and energy in our universe. You know, if you've ever watched a complex physical system in motion and wondered how on earth scientists actually calculate what's going to happen next, well, you're in exactly the right place. Today, we're cracking open Chapter 8 on potential energy and the conservation of energy, and we're going to see how visualizing energy simplifies, well, almost everything.
Seriously, imagine trying to calculate the exact speed of a falling bungee jumper at every single millisecond using standard forces. You'd have to account for gravity, the constantly changing tension of the cord as it stretches, air resistance. Honestly, it would be mathematically exhausting. But thankfully, physics provides us with a remarkably straightforward shortcut. Instead of tracking every messy intermediate step, we can just track the energy.
Here is our roadmap for this explainer. We'll be hitting the energy bank account, conservative versus non-conservative forces, gravitational and elastic potential energy, conservation of mechanical energy, reading potential energy curves, and lastly, the law of total energy.
Okay, part 1, the energy bank account, where we're framing energy as currency.
It's kind of wild to think about, but the universe literally treats energy exactly like an electronic transfer of money between two bank accounts. When we talk about doing work in physics, the term can actually be a bit misleading. We're not talking about physical labor where you just get tired pushing a heavy wall. Work is simply the act of transferring energy into or out of an object's account. And just like a digital wire transfer between two banks, the number in one account goes up while the number in the other goes down, with absolutely zero physical material passing between them.
Moving to Section 2, conservative versus non-conservative forces. Basically the rules of the transaction.
To manage these continuous accounts, the universe uses two highly distinct types of forces to process transactions. Think of conservative forces, like gravity or the snap of a spring, as perfectly reversible transfers. Like if you toss a tomato straight up into the air, gravity does negative work to slow it down, effectively taking energy out of its kinetic account. But as it falls back down, gravity puts that exact same amount of energy right back. The net work on a round trip is exactly zero. Non-conservative forces, on the other hand, they're like kinetic friction. They permanently charge an irreversible transaction fee. When friction slows down a sliding block, it transfers that kinetic energy into thermal energy, heat. You can't just, cool the block down and expect it to magically start sliding back the other way.
Section 3, gravitational and elastic potential. Think of these as the vaults of stored energy.
When those perfectly reversible conservative forces do their work, they stash energy into specific, highly secure vaults known as potential energy. Our first vault is gravitational potential energy. This is the energy associated with the state of separation between two objects that attract each other, like our bungee jumper and the Earth. The formula here, U equals mgy, shows that this stored energy strictly depends on the vertical position, or the height, between the object and the Earth's reference point. It literally doesn't matter if the jumper moves left or right, it's all about that vertical drop.
Our second vault is elastic potential energy, which is all about the state of compression or extension of an elastic object. Think back to that bungee cord. The amount of energy stored in this specific vault is determined by the spring constant K, which is just how stiff the cord is, and the exact displacement X, meaning simply how far that cord actually stretches from its relaxed length.
All right, part 4, conservation of mechanical energy, the perfect balance.
So what actually happens when an isolated system relies entirely on those conservative force faults? Well, our total mechanical energy becomes simply the sum of our active kinetic account, the energy of motion, and our stored potential account. As long as our system is totally isolated from external forces and completely free from the non-conservative drain of friction, this total mechanical energy is incredibly special.
Imagine tracking this with neon energy bars. Your kinetic and potential energy bars would be wildly fluctuating. Picture a roller coaster plunging down a hill. Its potential energy bar empties out fast, while its kinetic energy bar fills right up to maximum. But if you had a third bar tracking the total mechanical energy, it stays perfectly frozen in place. The energy is just rapidly shifting back and forth between the first two bars.
And this concept captures our absolute ultimate physics shortcut. Because this total sum cannot change, it allows us to instantly jump from an object's initial state at the top of a hill straight to its final state at the bottom, without calculating all the messy intermediate motion in between. You literally don't need to know the exact slope of the slide, you just set the initial energy equal to the final energy, and boom, you have your answer.
Section 5, Reading Potential Energy Curves. We're looking at holographic topography.
We can actually visualize this entire dynamic. Imagine a curving line representing a landscape of potential energy hills and valleys. Now draw a flat, horizontal line straight across it representing our fixed, totally static mechanical energy. Here is the big question. If our total energy line is fixed, what happens when the shifting potential energy curve rises up to hit that line?
That intersection is called a turning point. Remember, kinetic energy is just the difference between the total energy and the potential energy. So, when the potential energy rises up to perfectly equal the total mechanical energy, the kinetic energy account runs completely dry. The particle's speed drops to absolute zero, forcing the object to stop and reverse direction. It is physically trapped by its own energy limits.
Furthermore, wherever the slope of that potential energy is totally flat, the net force acting on the particle drops to zero. We call these equilibrium points, and they come in 3 distinct flavors. Neutral equilibrium is like a marble resting on a flat table. It just sits there. Unstable equilibrium is a peak, like a marble balanced perfectly on top of a bowling ball, one tiny nudge and it accelerates away. And stable equilibrium is a valley, like a marble resting at the bottom of a bowl. If you push it, a restoring force just brings it right back to the center.
And finally, Section 6, the law of total energy. It's time for the final audit.
Now, most actual systems aren't perfectly isolated, right? They interact with outside forces all the time. For example, think about a traditional blanket toss. That's a relatively isolated, conservative system. As the person ascends, kinetic energy perfectly transfers into gravitational potential energy and then reverses on the way down. But consider a rock climber rappelling down a cliff. They are doing something entirely different. They deliberately wrap their rope around metal rings to introduce non-conservative friction. They are intentionally bleeding their gravitational potential energy out of the mechanical system, transforming it into thermal heat on those metal rings. Because if they didn't do this, all that potential energy would become kinetic, and they'd accelerate dangerously straight into the ground.
Which brings us to the grand overarching rule of the universe. When we audit the total system, the exact work done by an external force will always flawlessly equal the combined changes in the mechanical, thermal, and internal energy accounts. Scientists have tested this endlessly. Energy cannot magically appear or disappear. Every single joule is meticulously accounted for in this final equation.
And that leaves us with a truly fascinating conclusion to this explainer. See, the entire universe itself is the ultimate isolated system. Energy within it is perfectly conserved, never lost, merely transferred. But with every non-conservative interaction, every single slide, every rub, every collision, a tiny fraction of our usable mechanical energy is irreversibly taxed away into thermal heat. So if energy can never be created or destroyed, just changed in form, what is the ultimate fate of our cosmic bank account when all the useful energy is finally spent? Keep that in mind next time you see a bungee jumper take the plunge. Thanks for joining me on this deep dive, and as always, keep your curiosity focused.